Hello everybody and welcome to Pytorch Deep Learning with Pytorch tutorials video series. This is the fourth tutorial here, and we're going to be going through a few different things. Let's start with this, which is the difference between a scalar, a vector, a matrix, and a tensor. This is an important concept. These are four different types of storage of numerical values. The scalar is a zero-dimensional unit. The vector is one-dimensional. The matrix is two-dimensional. Let me use my laser pointer here. Okay. And the matrix is two-dimensional here. It has two dimensions. And then a tensor is three-dimensional. Now, a tensor can actually be more than three dimensions. We can go to four, 5, and to as high of a dimension as we want. And it's a little bit harder to visualize, but it is still possible to cross into those dimensions. Now, when we're storing data, it's going to come in one of these forms. And an interesting thing to note is that if we're storing an image, a pixelated image, we will have length and width in pixels. So that is two dimensions, length and width of the pixels. Now each of those pixels will have a certain numerical value. Let's say it's grayscale. Then it'll have a certain value for the amount of gray within that image, or it could be RGB. So this is a good display of a way to store the data from an RGB image tensor. It'll have a certain amount of red, a certain amount of green, and a certain amount of blue for every pixel. And that is the way that we store image data in the form of a three-dimensional tensor. And we're going to do some coding to further define this concept in a little bit. Next, I'll talk about some of the data types. So we have numeric, dictionary, Boolean, set, and sequence type. So a numeric data is simply a number, and that could be well, it looks like they spelled integer wrong here. This should be integer, not integer. It could also be stored as a complex number or a float. We can have dictionary, which is a specific type of Python code. We're not going to get into that too much. A Boolean is simply a true or false value. Then a set is also something a little different. And sequence types, we do use that a little bit. We're not going to talk too much about that today, but that can be strings. A tuple is just a group of two. Strings can be a way to store words and sentences and stuff like that, and lists as well. So mainly what we'll be discussing today is the difference between integers and floats and how that affects writing machine learning code or neural network code. So this is code from TensorFlow, and we're going to be working with Pytorch. So I'll show it to you in Pytorch, but this chart just kind of gives a good overview of the different integer numeric values. So what's the difference between an integer and a float? Integers and floats are two different kinds of numerical data. An integer, more commonly called an int, is a number without a decimal point. A float is a floating point number, which means it's a number that has a decimal place. Floats are used when more precision is needed. So it requires a certain amount of bits to store these, and you call them using these commands when you're writing a tensor. Like if you define a certain tensor, you can convert it as well from floats to integers, and there's certain issues that go into that. And also Boolean, again, is true or false value. So I will quickly talk about a wide overview of machine learning, or of neural networks, and some of the definitions that go into that. And we'll get further into this later maybe in chapter 4. Right now we're still in chapter 3, so we're still talking about tensors. But let's get these definitions out of the way, and we may go over them again. Epoch. An epoch is one iteration over an entire data set. So we're thinking about a neural network here, where we have an input layer, a certain amount of hidden layers, and then an output layer. We have training data that goes into our input layer, and it feeds through certain weights, and they sum up the weights, and it goes through a unit step function. In this case, it's a unit step function. This could be any nonlinear activation function. And all of the weights here will get updated, and our neural network will become configured based on our error function and our optimization functions, and it'll eventually be able to take in the inputs and spit out the desired output that we want. And to do that, we train the neural network. And essentially an epoch is one iteration over our entire data set. A batch is, due to the fact that we cannot pass an entire data set into the neural network at one time, we divide it into a number of batches. So say we have 1,000 images that we're going to feed into our neural network to train it. We'll feed it in batches of maybe 4 images at a time to speed up the process, but not put them all in there at the same time, because then that would not be a good training method. And some of the science behind neural networks, it's a very new field, is kind of touch and go. And Yann LeCun is a figure in neural networks and machine learning. He's been working on it for many decades, long before there was such a popularity around AI. So his advice is always very pertinent and very good. He says training with large mini batches is bad for your health. More importantly, it's bad for your test error. Friends don't let friends use mini batches larger than 32. So mini batches, one rule of thumb there is to not go higher than 32 at a time. So that's it. So you'll see that, when picking activation functions, when picking the amount of neurons per layer, or the amount of layers, or the optimization functions, there's a lot of rules of thumb out there. So it's not always easy to determine what the best one is, and so there's still a lot of experimentation, and that's why it's fun and exciting to get into this field. So an iteration is, if we have 1,000 images as a data set and a batch size of 20, then an epoch should run 1,000 divided by 20. So that's 50 iterations. So all of these are somewhat related. We have a batch size of 20. An epoch is one run of all of those. So we iterate 50 times. We iterate the training process 50 times in order to reach one epoch. And there are ways to determine how many epochs you can run, and we'll see that later, because you can see when your solution begins to converge, and you look at your training error and your test error to determine when you are beginning to cross into the realm of overtraining. And we can also get a good value of our learning rate as well. So there are some things that we can define, but some things that are still, there's a lot of experimenting between everything. So now let's get into the coding here, and we'll do that with this code here. And let me pull up my code. So let's go ahead and import Torch. Okay, so now we have Torch inputted. Let's define an image T, we will call it, and that will be torch.randin. So random numbers, 3, 5, and 5. Trotch is not defined, so we will call that Torch. So now we have image T. Let's define another one as well. Let's define weights. So these were the weights in our neural network. So now we have an image, and we also have weights. I keep misspelling that. Tensor 0.2126. So we can run that code now. And let's look at our weights. That's it right there. It's a tensor. Let's look at our image tensor. And that's what it looks like there. And we saw the image tensor right here. So it's a three-dimensional tensor. And here it is, three-dimensional tensor. One value for R, one value for G, one value for B, length and width, whichever way you want to call it there. Okay, so what if we have a batch of images? Let's say our batch size is 2. Okay, so batch of T would be torch dot rand, and what would our values be? We're defining a tensor. We're going to define the shape here, so it's actually going to be 2 images, 3 values here for the RGB. Our length is 5 and our width is 5. And now we just created a batch size of 2 images here. If we look at that, we can see it here. We can see the 4 brackets signifying that we are now in a 4-dimensional tensor. So a stack of images, we have to cross into the 4th dimension in order to properly define it. So here is one image, pixel values, and here is another image. Another image's pixel values. So let's say image gray naive equals image t dot mean of the -3. So if you remember last time we did certain things with saying -3, that'll go to the -3rd dimension of it, and that's called indexing, if you remember. So we could also say, let's do this. So I'll prove my point here. Image gray naive, and so we're taking the mean of image t. So let's print this, just so we have a really concrete understanding of what we just did there. If we print that, and we also print image t, you'll see that our value in the first, in 1, 1, is 0.1382. This value, this is the tensor image t. We simply took the average of this number, and this number to get that. So this plus this divided by 3 equals that. And if we look at them, yeah, that seems about right. I'm not going to type it out to show you, but you could do it yourself if you want to prove to yourself that that's what we're doing. But let's say we, instead of writing -3, because image t is a certain shape, so image t dot shape shows you that it's 3, 5, and 5. We could also just write 1 here, and we'll get the same thing. Same number there. So this number is -0.0227. If we write -3, because we're saying, oh, maybe 1 wouldn't be the right way. Oh, 1 wouldn't be the right way. I made a mistake. It would be 0, because we start from 0. So now let's do it. -0.1382. And now we say -3. And we should, again, see 0.1382. Let's try it. Okay, so that's how we do that there. So the reason we say -3 is so that we get this dimension here, because you want your code to be pretty standard, to work for different things. It'll work for the image, but let's say we want to take the mean of the batch as well. So for that we would say batch gray naive equals batch underscore t dot mean -3. And now we can do that. So if this one we could put 0 in, and this one we could put 1 in, right? Because if we look at the batch, what is it, batch t dot shape, we can see that we have a 2, 3, we have 4 dimensions here. So we're going to the third from the last dimension. If we wrote 1, because we started 0, it goes 0, 1, 2, 3. Okay, and counting backwards, -1 would be this one, -2 would be this one, and -3 would be that one. So a little confusing, but it's not that hard to comprehend. All right, so in the last, or actually I think it was in the first lecture, we talked about this unsqueeze function, and we just kind of glossed over it. We said that's just something that you have to do. Don't worry about it. We'll talk about it later. So now we're going to talk about it. Let's unsqueeze the weights, and we'll just get a concrete understanding of what the unsqueeze function does. And if you're struggling to follow everything here, it is maybe because you don't have a good foundation in linear algebra. And I have a couple recommendations for linear algebra. If you wanted to tighten up your linear algebra. If you've taken a linear algebra class, I would say that is significant enough, and some of this stuff will come back to you as you do it, and you could just gloss back over things as needed. But the best course on linear algebra is, of course, from Gilbert Strang, a professor at MIT. And also, to top that off, this will teach you the fundamentals and go through a lot of examples, and you would be an expert in it. To get a good overview of linear algebra, 3 Blue, 1 Brown has great Essence of Linear Algebra series. It's very short. Each of the videos are like 10 to 15 minutes long, and it gives you good visualization of linear algebra. Those are, if you've taken a linear algebra course, then maybe this is what you would watch after taking that course, and to kind of wrap everything up and get really good visualizations. Actually, all of his videos are very, very good. So let me go back to our tutorial here, and let's look at the unsqueeze function. So we have weights, which is just a three-dimensional, or sorry, not a three-dimensional, it's a one-dimensional tensor, I guess you could say, but it's a one-dimensional, so that makes it a vector, if you remember from the beginning of the lecture. What is our unsqueezed weights shape? Unsqueezed weights. So we unsqueezed it. 2 dimensions, right? So we used to have just a one-dimensional vector. Now we have a 3-dimensional tensor. So why would we do something like that? Well, let's say we want to make a new tensor, and this one will be image t multiplied by our unsqueezed weights. Okay, so we can do that. We could also multiply our batch by this same tensor. So this is part of the process when these matrices or tensors are flowing through our neural network. They're being multiplied by weights, and then those weights will be summed. Eventually, we'll start calculating the error function, put in the optimizer, and that's how the internals of these neural networks work. We're just doing linear algebra. It's not the hardest mathematical procedure. The benefit of using machine learning or neural networks is that our computers can do all these calculations extremely fast. So but the calculations themselves are not beyond the capabilities of humans. We can do them and understand them. They're not. It's not quantum physics. So let me keep writing this code, and then I'll explain it after I get it written down. Batch gray. So this is the summing part, right? So we feed our weights through the neural network, and then at each node, all the previous weights are summed into each neuron. Let me pull that up just to show it to you again. That was on this slide. All of these inputs are being fed through, and then it is summed up at each neuron. Okay, so that's kind of what we're doing, just in a step-by-step process here. Okay, so we can run that. It works. You would get an error function if it didn't work. Let's look at the shape of all of these things. So batch weights dot shape, and I'm taking this code from the book that is in the video description, and I didn't know that we were able to do this, but it's kind of cool. You learn something new all the time when you're coding, of different ways to do things. We can put these commas in and get multiple things, so we don't have to type print. We can just write it like that and then get each of these listed out. So we have, what's the shape of our batch weights? That's a 2 by 3 by 5 by 5. What's the shape of our batch? It's a 2 by 3 by 5 by 5. And what's the shape of our unsqueezed weights? Well, we did that over here. It's a 3 by 1 by 1. So when we multiply our unsqueezed weights by our batch, the output is the same size. And what that's called is called broadcasting. It's broadcasting this one dimension. It's exploiting that the second dimension on it is 3, so those are matching. So we're able to have a matching dimension and broadcast it across the other dimensions. So the main lesson of this is, if you have one dimension that is matching, you can multiply those tensors. So what wouldn't work then? Maybe let's say that. Let's say we did batch T just by weights. We didn't unsqueeze our weights. We just did the batch T by it. That's not going to work. If we look at our batch T shape, it is 2 by 3 by 5 by 5. Okay. Our weights shape, let's run that over here, is 3. So it's saying, look, you have a 5 here and a 3 here. We can't do it. Okay. So, what if we just make a random tensor then? ABC equals torch dot rand 2. Let's try and spell everything correctly there. Okay. 2 by 1 by 1 by 1. Okay, so now we got ABC. Can we multiply ABC by our batch T? This is 2 by 1 by 1 by 1. This is 2 by 3 by 3 by 5. Let's see. We could just try it, right? Yes, we can, because this dimension is matching this dimension. If we change this to a 1, we cannot do it. Or a 1, we can do it. Because it's the same size. It's a 4-dimensional tensor. If we did this, I don't think we can do this. Oh, we can still do that. What can we not do? Maybe just because we're dealing with ones. Ah, okay. So when it's ones, it will let you do certain things. 2, these 2s do not match these 5s. 2 does not match 5, so we can't do that. If we said, and sometimes it's just good to play with these things and figure out what you can do. Let's try this. That doesn't work either. Okay. So I guess for when they're all ones, it allows you to multiply it. But in this case, we have all 2s, so we are not able to broadcast across that. So this 2 by 1 by 1 by 1 does let us multiply. If we have 1 and if we put a 5 here, then we can multiply them as well. So as long as the dimensions are matching and the dimensions that aren't matching are ones, then it should work. So if we put a 4 in here, it doesn't work. Right? Because this is a 3 and that's a 4. It has to be a 1 in order to broadcast. And you can look up broadcasting and see what that means to get a better understanding of it if that confuses you. All right, now I'm going to copy and paste something over here. We'll talk about the data types. I showed you TensorFlow code in the PowerPoint. This is Pytorch code. So if we want to call certain data types, because you will realize that a lot of your errors when you're applying a neural network to things are going to come from this, which is dimensions not matching, and data types. Like you got an integer 16 here, and you're trying to use a float 32 on it. It's not going to work. So when you're debugging your code, you're going to find that you're looking at the shape of certain tensors at various points and the data type. And remember, it's not hard to call your data type or your shape at any point. So I'm going to start copying and pasting some of this code here. Double points equals torch dot ones 10 2 data type d type equals torch dot float 64 torch dot float 64 or torch dot double. So if I want to, I could take this float 64 out and just write double, and I'm getting the same thing. So like I said, when you're debugging code, you can always do this. Like what data type was that? It is a float 64. Okay. What about short points? What data type was that? Okay, it's an integer 16. I mean, we literally just wrote it, so we know what it is. But in other cases, you might not. So in torch.short is right here. We could also do torch.int 16. Int 16, 32, 64. This is the amount of bits that are allocated to store this digit. Okay, so that's a 16. So this 1 and 2 and 3 and 4 is all stored in integer 16, and this 10 and 2. So if we just wrote double points, I believe that's a 10 by 2 matrix. Yeah. Of ones, of all ones, because we said torch.ones. So 10 rows by 2 columns. Float 64. Okay, so let's keep moving on here, and I'll just show you. I'm just going to copy and paste this because it's not super important, but there's other ways to write the same thing. And if you like this way, just stick with that way, and you'll be fine. But just you got to kind of know that you could also write it like this: double and short, dot double dot short. We're going to get the same thing. So let's double check that. it's a float 64. By putting this here, you get the float 64. If we did a half, let's see what that does, if that works. Okay, so you get a float 16. So kind of the language of it is 32 is kind of like the normal value. 64, you're saying that that's double, and 16 is half. So, as you know, this is a computation. If you have a higher amount of bits allocated to each value, your computation cost will go up. I've seen it written in literature that you don't get that much of a benefit from going to 64. So a lot of people stay at 32. In some cases, they'll drop to 16 and not see a significant decrease. So it's always going to be different. Like I said, some of the science here is kind of touch and go. So now let's keep moving forward here, and there is actually another way to write this. So I'm going to copy and paste that again. So if all three lines of this code are doing the same thing, and I will highlight what I mean by that. So this is identical to this and is identical to this. We are specifying the data type in three different ways. Dot to torch double. Okay, so now let's talk about multiplying two matrices, and I'll start writing it again because this gets a little more important. Points underscore 64 equals torch dot rand. So we got random numbers here. We'll say 5 comma d type equals torch dot double. So now we got a float 64 tensor of 5. It's a vector of 5, length 5, and it's just 5 random numbers at the end of the day, and they're stored as a float 64. Data type equals float 64. So let's write another line here. Points dot underscore short equals points underscore 64. So we are calling the tensor above, and we're going to convert that to torch.short or torch.int 32. No, short would be 16. 32 is the normal. So torch.short int 16. Okay, so let's go ahead and do that. So now we have 2. If we look at points, okay, so it converted it to 16. Can we multiply these two? Points by, yes, we can. If you weren't able to do this, this is a feature that works in Pytorch 1.3 and above. We're able to multiply matrices of different, or tensors of different data types. So that's 1.3 onwards. How do I check the version? I'm Googling it real quick, sorry. You can check your version using this line of code. So I'm in 1.7, Pytorch 1.7. Yep. So I'm good to go. If I had 1.3 or lower, I wouldn't be able to do this procedure. Another weird thing is these are all zeros, but we made a matrix of random numbers, right? So what gives? This is random numbers. So when we converted this torch of random numbers to an integer, it made them all zeros. because these are all decimal points. Okay? That's why. So when you convert, let me write print here. Okay, I don't know why it stores it different ways, but I like it stored this way. 0.6, 0.4, 0.6, 0.7, and 0.6. When we convert this decimal to an integer, the decimal is deleted, and all that's left is the integer. So it's all going to be zeros. Okay? So if we print points, all zeros here. Okay? So when you multiply 5 zeros by 5 any numbers, you get all zeros. Let's say we converted this to torch.float. It kept it, right? It only stored 32 of the decimal places. And if we say, what D type is that? What was float? It's a float 32. Okay, so if we multiply these now, points, we can multiply them and we don't get all zeros. So just something to note there. And I think that just about wraps up everything I have here. So that now we understand the different data types and also the shape. We're going to be using that a lot. So what's the shape of it? It's 5. Just remember these two. These are always very important. And next we're going to be talking about how the computer actually stores these tensors and talking about what we would call indexing into storage and the stride of a matrix, and that's basically how it stores it and understands what the shape actually is. And we'll talk about transposing and other things as well. So I'll see you in the next lecture. Thank you for watching my videos here.